Hello, everybody. My name is Philip Parnemitz, and I'm going to be your lecturer for these two lectures on reasoning and problem solving and decision making. This year we're trying something new. We're trying to do this online, and one of the reasons is that I'm not in Stockholm this year to give the lectures. And so both Agneta and I will be very curious to hear what you guys think about this kind of recorded approach. And yeah, welcome to the class, and I hope you enjoy it. This first lecture is about reasoning and problem solving, and it's roughly divided into two halves. The first, we're going to talk about problem solving, and the second, we're going to talk about reasoning, right? And the problem solving bit is divided into roughly three smaller chapters. One, we're going through a little bit of history of how problem solving has been studied historically, and we'll use that to transition nicely into talking about insight learning and problem sets, Einstellung, and other phenomena. And then finally, we're going to talk about general problem solving from an AI approach and the role of expertise in problem solving, which has also been heavily studied. Then normally there would be a pause in the lecture if this was a live lecture, and then there's going to be a reasoning bit where we're going to talk about roughly three central phenomena in reasoning. One is the waste and selection task, second is confirmation bias, and the third is the base rate fallacy. First of all, let's talk a bit about what we mean when we talk about problem solving in a psychological sense. So, problem solving occurs when an organism's desired goal state is not immediately available from its current state. That is, of course, a bit of a mouthful, and on the next slide we're going to talk a bit about some of the terms that we need to kind of familiarize ourselves with in order to understand the literature on problem solving better. But let me give an example of two types of situations that would be examples of problem-solving situations in the sense that we're concerned with in this class. So an example which I think most of us can recognize is something like a case where I want to drink coffee and there is no coffee in front of me. So here I have a goal state, wanting to drink coffee, and that goal state is not immediately available for me, so I cannot just reach out and grab a cup of coffee right in front of me, but I have to somehow solve the problem of reaching my goal state. And that process of solving the problem of achieving my goals is what the psychological study of problem solving is concerned with. Problems, of course, don't have to be that mundane, such as drinking coffee, but they can be fairly abstract, such as the problem of I want to raise happy children. We can think about problems using a number of terms which will help us organize their characteristics in slightly better ways. So the first of these is goal state, and we already used the term goal state on the previous slide. And so the goal state is simply the desired end state that we wish to find ourselves in at the end of the problem solving process. So usually also we think of problems in terms of their goal states. We can think of something like I want to drink coffee is the problem of reaching the goal state of drinking coffee. I want to have happy children is the problem of reaching the goal state of having happy children. So once we have the kind of goal state or the problem kind of initially laid out to us, we can think of a few more characteristics of the problem. The first is what we can call the initial state. And by initial state, we refer to the situation that we ourselves as an agent currently find ourselves in. And this is important in order to situate ourselves in relation to the goal that we want to reach. So in the case of me wanting to drink coffee, my initial state will of course be one where I'm not having coffee currently and perhaps at a place where there's no coffee immediately available, leading to this being defined as some sort of problem for me. Then we can think about sub-goals. So sub-goals are smaller problems that I need to solve in order to solve the bigger problem. So essentially, if I want to drink coffee, and let's say I know there's coffee in the room next to me, then a sub-goal of my reaching the larger goal of drinking coffee would be, for example, to exit the room I'm currently in and going into the other room. So on my list, kind of, my main goal is to drink coffee, but then there's a sub-goal of moving into the other room where the coffee is located. And we can think about this, the possible sub-goals and the possible paths I could take to reaching them in order to reach the goal state as the problem space. So of course, the goal state for me of drinking coffee can be solved by going to the room next to me where there is coffee, but it can also be solved by going outside of the building and going to the local coffee shop. And the kind of space of these possible actions that I can take define the kind of problem space of the specific goal given my specific initial state. And we call a problem well-defined when the goal state, the initial state, the sub-goals, and the problem space are all knowable. And this distinction of a well-defined problem will become important again when we consider what is known as a general problem solver and problem solving in AI a few slides down later in this lecture. Examples of well-defined problems are, for example, beating an opponent in chess, pinning a candle to a wall, and finding a street in an unfamiliar city. In all these cases, the goal state, your initial state, the sub-goals, and the problem space are fairly easy to map, and therefore the problems are fairly easy to solve using different kinds of problem-solving procedures, which can be kind of algorithmically applied. However, there are many problems that aren't well defined. For example, usually we might not be highly uncertain about our initial state, highly uncertain about the kind of space that the problem is. The problem space might be hard to map. There might be many possible actions that we simply aren't able to consider. And we're going to think about a few of those cases later on in the lecture. And in those cases, we call the problem to be ill-defined. And examples of ill-defined problems are things like you want to be happy, you want to be successful, you want to write an essay, you want to change as a person. So in all these cases, you can think of these as being problems where there's vagueness or uncertainty. And one way of turning an ill-defined problem into a well-defined problem is to, for example, give clear definitions about, for example, what do we mean when we say happy, and thereby turning, for example, the vague goal state of happy into a concrete goal state of happy. Let's say I become happy when I get to live in a big house. In that case, the goal state transforms from this kind of vague notion of being happy to a clear goal state of living in a big house, for which there's a fairly well-defined problem space, a fairly known sub-goal, such as getting enough money to buy a house. Following that brief introduction, we're going to transition into a brief overview over two main historical approaches that have informed the study of problem solving and continue to be influential today. The first of this is a view coming from learning theory and historically from the behaviorist movement. And I hope that you by now are all familiar with behaviorism and basic learning theory. But if you happen to have forgotten something, a quick reminder would be that the behaviorists, people such as Watson and Skinner, they construed a theory of psychology where the idea was that we could explain human psychology without reference to mental states or mental entities. So the idea was that it would be sufficient to study an organism's environment, to consider the stimuli in that environment, and then consider what responses the organisms made to that environment, and without any reference to any intervening states going on in the, so to say, mind of that organism. And so a behaviorist approach to problem solving simply is that problem solving can be studied without reference to mental abilities. And another way of understanding this then is that behaviorists want to study problem solving as a form of trial and error learning. And another term for this is that the behaviorists study what we call reproductive thinking. And here reproductive means that the problem solver, when encountering a situation, a problem, is reproducing behaviors which has previously tried, and reproducing those, of course, that have previously been successful to some extent in that situation. So the idea is that problem solving is not a creative endeavor, but rather it's a question of rote learning and repetition, i.e. kind of reproduction of previous behavioral patterns. And this is very famously summarized in Thorndike's law of effect, and that is quoted here for you. Responses that produce a satisfying effect in a particular situation become more likely to occur again in that situation, and responses that produce a discomforting effect become less likely to occur again in that situation. So what the law of effect is basically stating is that if I eat a piece of chocolate and I like it, I'll be more likely to eat a chocolate again. And if I eat a piece of chocolate and I don't like it, I will become less likely to eat a piece of chocolate again. And transferring that simple insight, and this is just, of course, basic learning, and you'll recall some of this from lectures on emotional learning, for example, and stuff about fear learning that you've learned in your first term. Then the idea here is basically that if I, for example, I want to drink my coffee and I choose the method of solving that problem by going into the next room and getting coffee, then the next time I want coffee, I'll be more likely to choose that particular behavior, i.e. going to the next room, rather than my alternative behavior, which was going outside of the building and going down to the coffee shop. Simply because when I went out to the next room, I found coffee there. But conversely, if I hadn't found coffee when I went to the next room, then I would be less likely to try that the second time around, and I'd be more likely to try the alternative, which would be going outside of the building. Okay, so basically the idea is that we try various solutions, and the ones that work, we repeat. To give an example of the kind of research that was done on problem solving in the learning theory or behaviorist tradition, we can consider Thorndike's famous puzzle boxes. And you see examples of the puzzle boxes in the pictures on the slide. And the idea of these puzzle boxes, as they're called, they were very simple puzzles or problems. And the problem consisted in that first of all, I should say that the research subjects in these experiments were cats. So you put the cat into the box, and the problem for the cat was that it wanted to get out of the box, because cats do not like to be confined into tight spaces. Of course, a behaviorist would never say that the cat wants to get out of the box or doesn't like to be in the box. The behaviorist would simply observe that for the cat it was rewarding to exit the box, and therefore it would try to produce behavior that would lead it to exiting the box, right? But we're not behaviorists, so we can talk about the cat not wanting to be in the box. So basically, Thorndike put cats into the boxes, and then the puzzle boxes were constructed in a way such that, I think you can see it kind of in the pictures here. I'm trying to highlight a few of these here, kind of string lever type mechanisms. And what essentially the boxes were constructed so that if you pulled the string with your paw, essentially, since you're a cat, a trap door would open, and then you would be able to escape the box. And what Thorndike observed was that, you put the cat into the box, it doesn't like it and starts, thrashing against the walls or trying to get out. And after a while, it'll, perhaps by chance, touch the string and the trapdoor will open, the cat will escape. Thorndike then puts the cat back into the box, and the cat tries to do lots of stuff again, but this time it'll be slightly faster at reaching the string and using that method to exit the box. And after a while, the cat will kind of learn this kind of association between pulling the string, the trapdoor opening, and being able to escape the box. And it will then, in the view of behaviorists, have learned how to solve this problem by it will learn this through trial and error. It will have tried various things, and of course, the kind of way that the cat learns this is viewed as evidence for the kind of law of effect formulation, i.e. that the cat is repeating behavior, i.e. pulling the string, for which leads to a desirable outcome for the cat, in this case, escaping the box. So basically, to sum up, on the classical learning theory approach, problem solving is a question of trial and error learning. So we try various responses, and then we stick with the one that works. But none of this involves any specific kind of creative thinking or restructuring of the problem space. It's essentially a question of having a clearly defined goal state and then trying various actions and repeating the ones that seem to have led to achieving the goal state. Gestalt theory provides kind of the polar opposite approach to that of the classical behaviorists. Gestalt theory was developed in the 1910s and 1920s, primarily in Germany, by researchers there. And then when the kind of Nazis took over in Germany in the 1930s, a lot of the Gestalt researchers emigrated or fled to the United States during the 30s and 40s and established themselves in American psychology departments. And those departments were at the time heavily influenced by primarily either Freudians or behaviorists. And they grew to have quite a big influence on the development of American psychology. And the kind of emigration of Gestalt theorists to the United States is to a large part responsible for the kind of growth of cognitive psychology later in the 50s and 60s. And you could think of Gestalt theory, Gestalt psychology as sort of a very early prototypical form of cognitive psychology, and they were working in a long-standing German tradition of being interested in kind of the function of perception in the human mind and in human psychology. And what was very special about Gestalt psychology is that it's had a strong emphasis on a holistic view of cognition. And this is sometimes summed up in the slogan that the whole is greater than its parts. And this, in part, led for the Gestalt psychologists to hold a productive view of problem solving rather than as you recall from the previous slides, rather than the reproductive view that the learning theorists have. So for the Gestalt theorists, problem solving was a creative endeavor. It was a question of putting together parts, and these parts could be, of course, stimulus in your environments, things you know about the problem, and then reaching a solution which, when you see it, kind of becomes more than constitutive parts. It's the idea is that when you solve a problem, you have an understanding of the problem which you didn't have before, and that path is a particular productive cognitive process. And to get an idea of kind of the perceptual work that Gestalt theorists did, which kind of you can think of by analogy to problem solving, is this kind of example of the Necker cube. And it's called the Necker cube from the researcher who first, I don't know if he actually invented this cube, but first drew attention to it as an interesting perceptual phenomena. And the idea with the Necker cube here is that the lines, of course, are on a two-dimensional surface, but to us humans watching it, it takes the form of a three-dimensional cube. So right there, kind of the whole image, the percept that we're having is greater than the kind of two-dimensional parts in a sense. But also what is very special about the necrocube is that it is what we sometimes call a bistable image. And by bistable, we mean that we can usually see the necrocube as being a cube where this bit here is to the front, and this bit here is the back of the cube. But you can also kind of switch your vision where the orange bit is to the front and the yellow bit is to the back. And if you stare at this cube long enough, you can kind of switch between these views back and forth, but you can't really entertain both views at once. And that's what we mean by being a bistable image. But when it comes to actual problem solving, the Gestalt theorists are primarily credited for introducing the word insight into the psychological literature, and this is a very, very important contribution, and we'll be talking a lot about insight later on in this lecture. And this is work primarily credited to the researcher Wolfgang Köhler, and he wrote a fantastic book, which I think is available still in most libraries, and it's definitely a worthwhile read if you ever have the time to spare. So what Köhler was doing, he was also studying animals, but he wasn't studying cats like Thorndike. He was studying chimpanzees, which are one of our closest primate relatives, of course. And he was testing a specific type of problem in particular, or he's famous for studying two problems, in fact. One is the one depicted on the left image here. And in this type of problem, the banana, which you see kind of here, is kind of hung from a string in the ceiling of a large room. And then in this room, there are a number of boxes. And of course, the chimpanzees cannot reach the banana at the onset. But after a while, what happens is that the chimpanzees kind of start moving the boxes around and stacking them on top of each other and reach the banana. The other very famous demonstration is involving the monkey Sultan, which is depicted here on the right image. And Sultan had a problem where he was also to reach a piece of food which was placed slightly out of his reach outside of his cage. And then there were a number of sticks put into the cage, and you can see two of them kind of on the picture here. And the important thing here was that none of the sticks were long enough by themselves to reach the piece of food. But if you kind of put the sticks together, then you can reach the piece of food. Now, you might be thinking, well, so what is different about this type of problem solving than to normal trial and error? I mean, you try things and then you kind of reach a solution and repeat that solution. Well, so what Köhler described in these studies is that, and this is his claim, that apes demonstrate insight during the solution problem. And what is meant here is that the chimpanzees would not appear to be doing something that we can be predicted from a behaviorist account. They weren't like trying lots of things and then failing in them and then trying at things that eventually worked. Rather, he would observe the chimpanzees, and they would kind of, first of all, define their kind of problem space, and they would realize that they cannot reach the piece of food by themselves, and then they would kind of sit and appear to think about the problem. And of course, already here you can see the large difference in this approach compared to a learning theory approach. And then suddenly, the chimpanzees would either stack the boxes or take the sticks and put them together and solve the problem in one go. And this kind of radical reorganization of the problem space is what Color called insight. And he claimed that this was a radically different way of solving a problem than simply solving it by trial and error or by experience or brute force. So insight then is defined as a sudden reorganization of the way a problem solver organizes a problem space, leading to an understanding of the problem conducive to solving it. So the idea is that you might have one understanding of the problem space. For example, I have to jump up and down to reach the banana. And then suddenly you reorganize the problem space, and reorganize the problem space here might be understood then as sending up alternative sub-goals instead of kind of jumping as high as possible as a sub-goal to reach the ultimate goal of reaching the banana. A sub-goal might instead become grab the boxes and raise my height so that I can reach the banana since I cannot jump high enough. And of course, then a lot of work has been dedicated, and we're going to review some of that work later on, looking at how humans both use and fail to use insight learning in their as a problem-solving strategy. And important questions for you to consider, that we'll be considering over the course of the next few slides, is do we often use insight to solve problems, and how can we facilitate insight? But before we leave this kind of historical overview, I want to look at one more animal, and that is the crow or the raven. And generally, this type of birds, known as corvids, are known as excellent problem solvers, and especially in the domains of causal or physical reasoning. So reasoning about how, if I use one object to interact with another object, how will that object, for example, move? So if you can think of, for example, corvids would be excellent pool players if they could use pool sticks and understand the rules of the game, because they're very good at understanding, for example, how an object moving would affect another moving object. So what I want you to do now is to go to this link here, and you can access that through the PDFs of the lecture slides. And then look at that, and then come back here and we'll talk about it briefly. So welcome back, and hopefully you have watched the YouTube video. And the reason why I wanted you to watch that video is not only because it's obviously a very cool demonstration of animal problem-solving skills, but hopefully you were able to observe the animal kind of using a mix between trial and error and insight learning strategies. So as the video presenter mentioned in that video, the bird was highly trained on each of the tasks, meaning that the bird had learned what the appropriate problem-solving strategy in each particular case, but the bird, of course, not seen the larger problem. And you can kind of see evidence of this early on in the video, when the bird is kind of, it grabs a small stick and then it goes to the rocks, takes one of the rocks out, but then it kind of gets stuck. It doesn't really know what to do, because normally when it solved one of these problems, it would normally kind of use a stick to get something out of the cage, and then it would get a reward for that, right? So the problem would end, and that was kind of the learning sequence. And then, and the presenter kind of highlights this also in the video, that it appears that the bird is kind of stuck and it's kind of considering what to do. And here it seems to demonstrate what definitely the Gestalt theories would call insight. It kind of, it's as if the bird is really abstractly reorganizing the problem space, and then it sets about solving the entire problem in one go. And what the bird is actually doing is, of course, highly complex and definitely beyond the scope of this course. But what I want you to think about, and a very important lesson to take home from that, is that it's not that Gestalt theories are right about problem solving and behavioral theorists are wrong about problem solving, or vice versa. These are kind of theories, or you can think about the models of problem solving. They focus on one aspect of the problem solving situation and then try to construct studies where they'll kind of bring out those features and be able to study them and propose them. And a lot of psychological theories, and this is an important point, a lot of psychological theories function the same way, such as that they highlight one aspect of the psychological process that the theorist is interested in, and then of course the psychologist and the researcher will construct experiments to investigate what is predicted by that particular theory. But of course, in an ecologically valid situation, for example, humans solving actual real life problems, we'll always be using a mix of strategy. We'll be using some insight, we'll be using some trial and error learning, and other possible strategies. And that's important for you to keep in mind, not only for this lecture, but for all psychological theories that you will encounter over the years. So a lot of work in human problem solving has progressed by identifying various types of effects where humans either fail to solve a problem or solve a problem less efficiently than they optimally should be able to. One such effect is known as Einstellung, and that's sometimes also called problem-solving set or entrenchment, and you'll see kind of all three terms being used in various books and pieces of literature kind of interchangeably, and we'll definitely be using them interchangeably in this course. So Einstellung occurs when a problem solver gets stuck in a particular mode of solving a problem, even though better solutions exist to that problem. So this is a case where the problem solver is solving the problem, but the solution that's being used is one that is simply not as good as other solutions. So it's a case where you could imagine, if we reflect back to the distinction that we've been working with between trial and error learning and insight solving, where the problem solver has tried something and it's worked and therefore continues to use that solution, but where if the problem solver would kind of take a step back and reorganize the problem space, I get an insight into the problem, a more efficient solution would exist. And to get a clear idea of this, we'll discuss an example, and this example is called the water jug problem, and the water jug problem was formulated in the original studies that kind of introduced the Einstellung effect and give a very good demonstration of how it works. So in the water jug problem, participants are faced with the idea that they have 3 water jugs in front of them, and they can fill them with water, but they can also fill them completely with water, and then their goal is to make sure that in at least one of the jugs they have some desired quantity of water. So if we consider the first problem here as an example, the idea is that they have a jug A with 21 liters capacity, a jug B with 127 liters of capacity, and jug C with a capacity of 3 liters. And the idea is to get 100 liters into one of the jugs. And hopefully you can see the solution fairly simply. And the solution to this problem, for example, is by filling jug B with 127 liters, then filling jug C with 3 liters twice and pouring out in between, meaning that you have 121 liters remaining in jug B, and then pouring 21 liters into jug A, which will finish you off with 100 liters in jug B, which was the desired quantity. Okay, that's the basic outset of the water jug problem. And when students or participants in experiments are given them, they're given, for example, these 10 problems shown here in sequential order, but you of course don't see all the problems at once, you get them one at a time. So all of the problems in the table that I just showed you can be solved with a general formula b minus 2ca, which was a solution we kind of walked through together. And as it also happens, this is the simplest solution for problems 1 to 5. And when typical participants are given this set of algebraic problems and they work on them in order, 83% will use this solution also on problems number 6 and number 7, where, and you can verify this for yourselves afterwards, there are simpler solutions than the b minus 2c minus a solution. And 64% fail to solve problem 8 because their b minus 2c minus a does not work at all. And then once again, 79% will use b minus 2c minus a on number 9 and 10. So this is an example of participants becoming entrenched in the one particular solution of the problem and then constantly applying that solution instead of rethinking the problem when appropriate. And of course, importantly, if participants are just given number 8 or given in this case the last 5 problems, only 5% fail to solve number 8. So if you don't have that much experience with problems where b minus 2c minus a is the simplest solution, then you won't be entrenched in that particular solution and be able to solve the problem in itself. So what this work shows is that entrenchment is something that can be induced into a problem solver, and it can be done so with fairly few trials of reinforcement. In this case, only 5 exposures to a typical optimal solution is enough to kind of entrench problem solvers to the extent where they fail then to rethink later problems of the same kind. Another particular form of Einstellung or entrenchment that commonly occurs in problem-solving situation is known as functional fixedness. And functional fixedness refers to entrenchment with an everyday or common use of an object. And a common example of this is in the Duncker-Kendall problem, which you are all familiar with by now. And there, of course, the functional fixedness refers to the role of the box in the problem. So the idea is that we might be fixated with the use of the box as a carrier for the tacks. One of the common kind of mistaken solutions to the Duncker-Kendall problem, of course, is trying to tack the candle to the wall with the tacks, which of course is not a valid solution to that particular problem. And the kind of functional fixedness with the box can be overcome in that problem, and has been experimentally demonstrated so by presenting the tacks outside of the box. So when the problem solver meets the Duncker-Kendall problem, the tacks are already outside of the box, and that somehow makes it easier for the problem solver to see the box not necessarily as an item to carry tacks in, but as a shelf, as is in fact the intended solution in that particular problem. We can also, of course, induce functional fixedness, and one famous demonstration comes in the two-string problem. And the two-string problem, and you'll see that kind of on the illustrated in the GIF here on the right-hand side. In the two-string problem, the problem that the problem solver faces is tying 2 strings together. And the strings are placed in a way so the problem solver can't reach them by holding one string and reaching for the other string. The solution is reached by tying one of many heavy objects that are presented to the problem solver at the same time to one of the strings, and then kind of using that string as a pendulum in order to reach the string while simultaneously holding the first string in the hand, as demonstrated in the GIF here. And well, what about functional fixedness? Well, so these everyday objects that are on the table, they can be anything really that's heavy and they'll work for the problem. In a famous demonstration of inducing functional fixedness, the experimenter gave the participants extra experience with one of the objects. So in this particular case, the heavy objects were various types of electrical engineering gadgets, such as switches and relays used to kind of complete electrical circuits. And the participants were first given a pre-experimental task of solving an electrical circuit. And in one group, the participants solved the circuit using a switch, and the other group solved the switch using a relay. And then, depending on which object had been used to solve the prior electrical problem, the participants would be more likely to use the other object as the kind of weight in the pendulum. So if I had solved the electrical circuit problem using a switch, that would induce functional fixedness, that switches are for solving electrical circuits, and that would mean that I'd become more likely in solving the two-string problem using a relay instead, right? But of course, a control group was shown to be equally likely to use either object to solve the two-string problem, because of course they didn't have that prior experience with one of the objects as having a function in electrical circuits, and therefore had no functional fixedness with those objects. One particularly interesting method that has been used to study Einsteinian problem solving has been by looking at eye movements during problem solving. And eye movements are interesting because the way we move our eyes is usually a very good proxy for what we are attending to and where we're directing our attention. And in this particular problem solving task, this was a word-based anagram task. And an anagram task, the goal is to, of course, rearrange the letters, an anagram, to make a word. And this particular version of the task, the goal was to make a 5-letter word from the central letters presented on a screen and 2 of the 3 kind of peripheral letters are being shown. So one of the letters is a distractor. And in this case, there was a word condition and a non-word condition. And you see the word condition at the top here, and then you see the non-word condition at the bottom. And participants were shown one such screen at a time, and these are just 2 examples of many stimulus items being used in this experiment. And participants' jobs was to simply solve the anagram and indicate when they solved it. And while they were deliberating, their eye movements were monitored so that the experimenters could see where they were looking at while solving the problem. And the main findings here was that there was longer solution times to words compared to non-words, right? And that's maybe not entirely unexpected. There was more difficult, in other words, to solve the anagrams when you're given a word, because the word kind of course entrenches you that the letters should appear in that particular combination in the final solution, which is of course not often the case. And interestingly, the experimenters found longer viewing times to the individual letters in the word compared to the non-word condition. So each individual fixation, each individual glance was longer in the word compared to the non-word conditions, and that's what you see on the graph down here. You can ignore the differences between pop-out and non-pop-out. These are just 2 different types of problems. The important thing is that as you can see, the white bars here are taller than the gray bars here. And the experimenters interpreted this effect, that it's harder to integrate individual letters to a new holistic entity in the word condition compared to the non-word condition. And this is particularly important because it suggests that kind of our entrenchment with a problem, or how we kind of are stuck in thinking about component parts of the problem that would lead us to a solution, is dependent on and guided by attentional processes. And if this is the case, then it should be possible to guide attention in a way to help a participant solve the problem. And that is precisely what the next study we're going to look at found. In this study, researchers investigated Dunker's tumor problem. And in the tumor problem, which you're also, of course, familiar with by now, recall that there is a sort of a skin of a kind of organism or whatever, and there's a tumor in the middle, and there's healthy tissue kind of on the outside of the tumor, and the problem solvers were told that the tumor can be killed by lasers, but if you and that small quantities of the laser won't damage the healthy tissues, but large quantities of the laser will damage the healthy tissues, and you need large quantities of the laser to kill off the tumor. And recall that the kind of the optimal solution then is to use many lasers focusing in from many directions, so that they all transcend on a fixed point here, and therefore there'll be enough laser focused on the tumor to kill it, but not enough laser to kind of actually damage the healthy tissue, right? So this research proceeded in 2 steps. First, the researchers used eye tracking to get kind of a descriptive baseline of how people look at the kind of visual depiction of the problem when solving the Dunker's tumor problem. And they compared participants who were successful with participants who were unsuccessful at solving the problem, and they found kind of significant differences between how much the participants in the last 30 seconds before solving the problem looked at the skin region of the diagram depicting the problem. So next, the participants tried to use this knowledge in a causal intervention. And participants were divided into 3 conditions. One was a control condition, so a normal tumor problem. And then there were 2 kind of critical conditions. In one, attention was guided to the skin, and this was with the help of kind of pulsating GIF animations. So the skin would kind of be kind of slightly pulsating or blinking, if you so will, so that the participant would be more likely to look at the skin. And then there was a kind of a foil condition where attention instead was guided to the tumor by the same method, so the tumor would be blinking instead of the skin. And what they found was, and that's shown in the table here, importantly, that only in the animated skin condition did the solution rates increase. So more participants solved the tumor problem when their attention was guided in this kind of manipulative way to the kind of bit of the problem which is supposed to give an insight into solving the tumor problem. So the important kind of lesson that was drawn from this research is that kind of task-related attentional shifts might facilitate insight into the problem. Of course, not all problems are visual in the way that the tumor problem is. So there are, of course, other ways to kind of guide solutions or insights into the problems. And one way that's been investigated is the use of analogies, right? And that by providing an analogy to the problem, that will aid a restructuring of the problem and kind of guide insight. So this has also been studied in using the tumor problem, but just a text version of it, so you don't get to see the actual diagram of the tumor like in the previous research that we just looked at. So here the idea is that participants are presented with a seemingly unrelated story, but the story is an analogy to the tumor problem. And in this particular research, the story was, it's called the Fortress story, and the story about a dictator that's holed up in a castle. So this is an analogy to the tumor being holed up in the cell. And then what the story describes a general kind of overcoming the problem of attacking the dictator by, in this case, dispersing all his troops around the castle and kind of overcoming the walls and kind of reaching the dictator from all sides and thereby defeating him. And this, of course, supposed to be an analogy then to how the lasers come from all directions of the tumor and destroy it. And importantly, this research kind of unsurprisingly showed that if participants read this story before reading the tumor problem, they will kind of, to a high degree, come up with the correct solution, which I'm highlighting in green here. But also, the researchers also gave other kind of stories about how the general defeated the dictator, and these were stories that kind of mirror common mistakes or common alternative proposed solutions that participants come up with to the tumor story, such as trying to do a complex operation, which was analogized by digging a tunnel under the castle. And the important result here is that the other stories that were presented to the participants increased the kind of frequency with which they gave the corresponding erroneous solution to the tumor problem. Right. So so it's not only that if you present participants with a story about a fortress and a dictator, that by analogy, where the dictator is defeated by analogy in a way that corresponds to the correct solution to the tumor problem, then participants will solve the tumor problem to a higher degree. But also, if you provide them with an analogy which shows a solution to the problem of the dictator, which by analogy would be a bad solution to the tumor problem, then participants will kind of use that solution to aid them in understanding the tumor problem. And of course, this is then another example of what we saw earlier with the water jug problem of kind of entrenchment, of kind of using one solution, but instead of using it in the same kind of problem, this is a case of analogical transfer. Okay. And also, a very important finding in this, in another follow-up to this study, is that these kind of effects were the largest when participants were told that there's something in the story that will help solve the problem. So, if participants are just given the fortress story and then told the tumor problem, not all participants will perceive that this is an analogy. But if you tell them that you're now going to read a story and this story will help you solve another problem, then of course more participants try to use that information to guide their thinking. We're now going to transition from talking a lot about insight problems and barriers to solving insight problems, and of course interventions that can be made to help solve those types of problems, to a different type of approach to study problem solving and a different class of problems. And we're going to do so by first introducing and considering the general problem solver. And the general problem solver kind of represents a very early cognitive science approach to problem solving. And the GPS, or the general problem solving, is an AI problem solving, so artificial intelligence problem solving, so a computer that solves problem. So this was developed by Newell and Simon, and they kind of proposed that this computer program that could solve very simple problems was also a model of how the human mind solves problems. So, and this is a very important historical lesson that kind of early cognitive psychology and early cognitive science, when it started developing in the 1950s, 1960s, and later in the 1970s, it started developing with a backdrop to the rapid development of computers, which of course was completely revolutionary at the time. And the idea was that computers, they have some sort of environmental input, usually from their keyboards, and they have a central processing unit and memory units, and then they generate some sort of output. So the idea was that, and computers can, do logical things, and humans can do logical things. So the kind of idea was that just like humans have some sort of environmental input, which the behaviors we call the stimulus, and generate some sort of output, or we would call the response earlier in this lecture, then it might be that the human mind is something like a computer. It has kind of a central processing unit and a memory, and this might be a kind of a working metaphor for the human mind. And of course, a lot of work in cognitive psychology, especially the early work, builds on this. The famous memory models by Atkinson Shiffrin, the kind of three-box models where you have a sensory processing, a short-term memory, and a long-term memory. They were all developed with a computer analogy in mind. What's important for the study of problem solving for our lecture here is that within this framework, then it made sense to kind of write a computer program that could solve problems, and then look at how that computer program solved those problems, and use that to make deductions about how humans would solve problems. And this work, I mean, so this might, depending on what your particular background is, this might sound very sensible to you, or this might sound completely silly. But this work helped, if nothing else, to structure our thinking about human problem solving. And in the kind of general problem solving framework, this is where the kind of terminology that I introduced at the beginning of this lecture was originally introduced. So the idea is that you define a problem in some sort of abstract problem space, wherein you find an initial state, a goal state, and then there are all the kind of intermediate states that make up that problem space. And then if the computer can map that space properly, it'll also be able to solve problems. And the way the general problem solver solves problems in this kind of abstract problem space is through something called means end analysis, which is achieved by searching the problem space. And what does this mean? Well, a means end analysis works by considering an action and its outcome, and then selecting that action if it kind of reduces the distance between the current state and the goal state. So the idea is here that the problem solver figures out its initial state, and then figures out its goal states, and then it considers all the possible actions it could take, and it, so to speak, imagines itself taking those actions, and then where it would end up being if it took that action. And it selects the action that would put it at the closest possible state in relation to the desired goal state. So if we go back to the very tired example of me wanting to drink a cup of coffee, one reason for me choosing to go to the room next door and getting a cup of coffee rather than leaving the building and going for a cup of coffee is that I can think of the number of actions I would have to take in order to reach the final goal state. And in terms of number of actions, if I go to the room next door, I kind of have to get out from the desk where I'm sitting, go to the room next door, and then there will be coffee and I'll pour it. If I go to the coffee shop, I first have to get out of my chair, but then I have to go a few stairs down, exit the building, go out on the street, go to the coffee shop, order a coffee, and then I get the coffee. So they're more kind of intermediate intervening states before I reach the final goal state. So the distance, and of course in this particular example I'm giving you, the distance is of course very neatly mapped into the number of steps kind of in meters I have to take to reach the coffee. But when solving a more abstract problem, the idea is that I have to do fewer kind of cognitive operations in order to reach the goal state. And this kind of way of kind of searching the problem state, as I just described, and this kind of coffee problem I've described to you, there are kind of two possible kind of actions that I can take to reach my final goal state. Then this means ends analysis is a very efficient way of solving the problem. However, if the number of actions and the number of intervening states is high, then this becomes very quickly computationally unfeasible, especially so in the 1970s when these theories were first proposed. But even today with super fast computers, kind of brute force searching a problem space is usually a highly inefficient way of solving a problem, even if it's not always necessarily as unfeasible as it was in the 1970s. So the kind of general problem solver theory and the computer programs that are proposed works well for very simple and well-defined problems. And examples of these are kind of the Tower of Hanoi and the Hobbits and Orcs problems, where they're kind of, 6 to 20 intervening states, and you can kind of search through all of them and figure out what the optimal solution is. So what the general problem solver then highlights is that strategies that work for small problems do not always work for large ones. And one way of getting around this is setting sub-goals. And sub-goals is just another way of dividing up a big problem into smaller problems, which might have a smaller problem space, and therefore might be possible to search them exhaustively and figure out what the best solution is. And a lot of work in computer science, of course, has been devoted to understanding how we solve problems like this, and to some extent humans do this naturally all the time. If you think of a very large and difficult problem like getting a good grade, then you might divide that into smaller sub-goals, which would be, for example, attend all the lectures in my course, read all the assigned readings, do all the practice exams, spend 1 hour each evening studying, and then study intensely for the exam, and then sit the exam, and then reach the ultimate goal state of getting a high grade. And then each of those kind of sub goals, then you can probably figure out how to achieve them the best way. So, for example, attending all the lectures might be achieved by for example, setting your alarms early in the morning, if you have morning lectures, etc., etc. And what the kind of work on the general problem solving has highlighted is the importance of expertise. So early attempts to apply these kind of AI or software problem solvers was often used in medical decision making. So the idea was that you would give the computer program some symptoms, and then that, of course, the problem, the goal state is giving the correct diagnosis of these symptoms. And of course, it was found that this was, the problem solvers were greatly helped if you coded it with using expertise available from doctors and the medical literature to help it kind of set the correct sub goals to kind of search the problem space efficiently. And this kind of understanding that expertise matters led to psychologists realizing that in order to understand human problem solving, we probably have to understand expertise and study how experts solve problems compared to novices. And one domain where this has been heavily investigated is the game of chess. And this is because chess is a well-defined problem in the strict sense of the word. And of course, computers, chess-playing computers have been around forever. In the 70s and 80s, they were good and could beat novices, but not experts. Of course, nowadays, chess has been, something that computers can beat us in for 10, 15 years now, and nowadays, of course, very recently, the DeepMind AIs have beaten humans in far more advanced games, such as Go, and of course, the importance of beating humans in these kind of well-defined games harks back to this work on the general problem solver and the work of kind of understanding expertise in well-defined problem domains. So over the next few slides, we're going to look a bit about research on how human experts solve chess problems. So one of the early and most influential papers on chess masters and how chess masters differ from novices was work done by Chase and Simon in the early 1970s. And what they did was that they showed participants chessboard configurations like the ones shown here on the right. And these chessboard configurations would be either configurations that could actually occur in a game of chess, or they could be kind of random configurations that could not occur in a real game of chess. That was just the result of randomly putting the pieces on the board. And what they found was that chess experts remembered actual configurations significantly better compared to novices. So when they were looking at these kind of real chessboards, they could later put more pieces correctly on the correct square on the chessboard than novices. However, when viewing random configurations, there was no difference between experts and novices. And this is important for two reasons. One is that one kind of hypothesis of what makes someone, for example, a chess expert, could be just that they have a natural superior memory, so that they just remember various board game configurations and therefore become good at chess. Right? So, but if they just had a general kind of unspecifically good memory, chess experts would be better than novices, regardless of what kind of board you gave them. But of course, the findings were that chess experts were better at remembering actual chessboard configurations. So that shows that they had acquired a certain domain-specific memory and specific knowledge. And Chase and Simon dubbed this perceptual chunking. So the idea is that chess experts don't have a kind of higher memory capacity than average people, but they're better at chunking the pieces of information into meaningful wholes. In other words, they're better at compressing the information in a way that allows them to remember far more details when they're unpacking that information later. And an important consequence of this in terms of the kind of problem state formulations that we were dealing with in the previous slides is that if you kind of make a good compression of a problem state, you also highly reduce the complexity of the problem state. I.e., in other words, by reducing kind of remembering these kind of 64 different spaces into a meaningful chunk, such as, for example, the tower here is threatening the horse, and then the next tower, and remembering that as a relation rather than remembering on the first square there is a white tower, then there's an empty black square. That reduces kind of how the complexity of description of the state, and therefore also the complexity of any operations that need to be done on that state in order to figure out what the next optimal action is. There's other more recent work also showing how chess experts and novices differ when looking at configurations of chess pieces, and this is work once again using eye tracking. And so what the researchers did here was that they compared novices, intermediates, and experts, and had them look at these kind of piece configurations. And what they found was that novices would make far more fixations per trial than experts, and that even when making multiple fixation, experts would make less complex scan paths. So they would kind of look around the board in a fairly straightforward manner, and you see this also with the intermediates, whereas novices will kind of be looking all over the place. And this gives additional evidence that part of what it is to acquire expertise in a domain is to kind of learn to chunk and organize the information that you're getting into more meaningful wholes, and using those, and then you can use those meaningful wholes to make more efficient operations, and therefore solve the problem quicker or more effectively, since you have to go through fewer operations in order to actually reach the goal state, which of course for highly complex problems means that you this might mean the difference between solving the problem and not solving it at all, which is of course the case for chess players, where novice chess players rarely solve the problem of winning the game, or expert chess players quite often solve the problem of winning the game. So to sum up where we have arrived currently in the lecture, we've reviewed a number of problem-solving strategies. We can gain insight into problems, and we can use various techniques to help us restructure the problem space, for example, by directing attention. We can engage in some means-end analysis. We can learn to set sub-goals, and of course acquire expertise in the particular domain. And all these, of course, useful techniques and ways to solve actual problems. And here I just want to remind you that, of course, human beings in their natural habitats, echoing a point we made earlier, of course, use a mix of these kind of strategies in going about their daily lives. And finally, of course, another way of solving problems, something that's kind of been implicit in some of the accounts that we've been looking at so far, is to apply reasoning and heuristics, i.e. to think and reason actively about the problem, or apply heuristics, and we'll talk about what that means to solve problems. And so now this lecture is kind of going to transition into talking about reasoning and human reasoning abilities, but and this is something that's been studied as a separate literature to the problem-solving literature. But I want you to keep in mind that these are, of course, very interconnected cognitive processes, and understanding one helps understand the other. To begin with, we can distinguish between two types of reasoning. One is inductive reasoning, and inductive reasoning is characterized in that it starts off with specific observation and then attempts to generalize to a general proposition. So, for example, one might make an observation that this drink is a cup of coffee, and then the next observation, this drink is tasty, and from there try to make the generalization, all coffee is tasty. And importantly, this is not a logically valid form of reasoning, but of course it's a very important form of reasoning, and a lot of scientific reasoning is of this kind. And indeed, I mean, the kind of reasoning that the sun will rise the next day is a form of inductive reasoning. The sun rose yesterday, the sun rose the day before that, etc., etc. Therefore, the sun will rise today. And another type of reasoning is deductive reasoning. And deductive reasoning starts with a general proposition and then reaches specific conclusions through the use of logical rules. So start with some sort of general proposition. All coffee is tasty. And then you make a specific observation. This is a cup of coffee. And then you reach a general a specific conclusion, such as this drink is tasty. And this is, of course, logical. If you follow the logical rules, the idea is that then this is philosophers will call this truth preserving. So you can be certain in the conclusion that you reached. And logical reasoning or deductive reasoning is something that humans throughout the ages have thought that we are particularly good at, especially compared to other species. And of course, the Greeks, for example, thought that one of the hallmarks of humanity, they even defined humanity as being the rational animal, and rational here meant was capable of deductive or logical reasoning. And of course, for psychologists, this has been very important as well, because for reasons as I explained earlier in terms of understanding the human mind by analogy to a computer, computers of course very good at logical reasoning, and one of the reasons we thought computers would be a good model for understanding the human mind was that the humans were thought to be very, very good at deductive reasoning. Therefore, a lot of psychological work and a lot of important psychological work has been devoted to studying how humans perform deductive reasoning tasks. And we're going to look at, we're going to start off by looking at one of the absolutely most important examples of that, and that is the Wason selection task, and discuss what the findings there mean for understanding of deductive reasoning and human reasoning capacity. So we'll first quickly review the Wason selection task, and you've already seen it in your lab. But so here's the basic setup. There are 4 cards. You're told that each card has a number side and a letter side, and then you're asked to indicate which of those cards you would need to turn over in order to judge whether the following rule is true. If a card has a vowel on one side, then it has an even number on the other side. Okay, and as you probably recall, the normatively correct responses here are the A card and the 7 card. So the rule here has the logical form of if P then Q. So if a card has a vowel, then it has an even number on the other side. And the logically valid way of testing this rule is to attempt to falsify it. So in order to try to figure out a case where the rule would make a false prediction about the state of the world, i.e. the state of the cards that you can turn up and down. And the way of doing that logically is by examining the P card. So the P form here of the rule, and turning over that. So if you turn over that and it has an odd number, then of course you falsified the rule. The other way is to turn up the not Q card. Okay, so you don't want to turn out the Q card, but the not Q card. So in this case, the odd card. So because if you turn over the odd card and it turns out that the other side of the odd card is a vowel, then you falsify the rule, right? Because the rule says that if there's a vowel, then there's an even number on the other side. It doesn't say that the rule doesn't say that all even number cards need to have vowels only that if it's a vowel, then it has to be even numbered. So if you turn off the odd number and see that there is a vowel or not, and that will help you falsify the rule. Now, in terms of logic, this is about as straightforward as it gets, if you ask a logician. However, most participants fail the Wason task, and in the first reports, 90 to 96%, and of course this varies a lot with what population you're testing, etc., etc. But generally, this is highly replicable. That most people find the Wason task to be quite difficult. And when this was first published, and this was in late 1960s, this was seen as completely devastating to the idea of human supremacy in the domain of deductive reasoning. So the idea is that human participants, and of course in most psychology experiments, the participants are undergraduates, college undergraduates, usually at elite institutions. So the fact that these highly trained, highly educated student participants would fail at this task was absolutely shocking at the time in kind of in the world of cognitive psychology and educational psychology, etc. And by extension, this is also problematic for our hopes of, for example, in terms of scientific discourse, because one of the dominant ideas in the philosophy of science in the 20th century, due to the philosopher Karl Popper, is the idea of falsificationism. The idea is that we gain knowledge in the science by falsifying theories. So the idea is that this has to do a bit with the distinction between inductive and deductive reasoning that we discussed earlier. So many scientific observations are inductive by nature. We observe many cases and then draw a kind of general conclusion of it. And from that general conclusion, the idea is that we form a theory about the world, and then of course then that theory makes predictions. And then since we can't be sure about the inductive step in reaching the theory, however, we can be sure about the predictions the theory later makes. And the idea in falsificationism is that we then go about testing our theories by trying to find observations that would falsify one or more of our theories, and that will help us kind of adjudicate between competing theories, not only psychology but in all sciences. So finding that humans are quite bad at falsifying theories is problematic for the notion of using falsificationism as a practice, like our hopes that people will be able to adopt this as a way of evaluating scientific theories. So there have been many extensions of the Wason task, and one of the most famous versions is the deontic version, which you also tried out at the lab. And here, if you recall, as a participant, you're asked to imagine that you're a police officer on duty, and you're trying to check that people are conforming to certain rules, and in particular rules about drinking ages. And then you're simply asked, you imagine that you have these 4 cards again, but these 4 cards represent different persons in a bar. And the question is, who would you ask in order to confirm the rule? If a person is drinking beer, then the person must be over 19 years of age. And here, of course, you would naturally ask the person who's drinking a beer and the person that's 16 years old. Right. And in this task, the deontic version of the Wason task, most participants succeed. So in the original Wason, most participants fail. Here, most participants succeed. And hopefully, you had that intuition when you were looking at these problems that the deontic task is much easier to understand. However, what is really important about this is that the rule has the same, or at least a similar logical form as in the original task. It's a form of if P then Q. So the claim here is that the Wason task might not be showing a sort of a general failure of our logical reasoning, but showing something else. So what the people who developed the deontic version of the Wason task tend to argue is they tend to give a sort of a evolutionary explanation. The idea is that people have been evolved to evaluate social rules, but not abstract logical rules. And this explanation isn't perfect by any means, and it's unclear why we should think that we evolved to evaluate, drinking age rules, and why that wouldn't generalize in that case to any other type of rule. But the data definitely is firm that humans have a much easier time at solving the Wason task when it's formulated as a social rule rather than as this kind of abstract rule. The Wason task can also be used to understand another feature of human reasoning called confirmation bias. This was in fact the original purpose for Wason when he was devising the task originally. And to understand confirmation bias, let's introduce it by looking at the response distribution of the original Wason task, which you can see here. You see most participants pick the A card, which is a clear test of the rule, and of course very few participants pick the correct combination of cards. But critically, if you look at the erroneous responses, quite a lot of them involve the 4 card. Almost half the respondents pick some combination involving the 4 card. And this is particularly interesting because the 4 card is an example of a logical fallacy called affirming the consequent. So remember, the 4 card is the Q in the if P then Q form of the rule. And the problem with picking the Q card is it adds no information to the rule. It will at best confirm something you already knew, which is that if you turn it over, then there might be an even card, and then you'll confirm the rule that you had. But the rule actually doesn't say anything that all even cards have to have a certain letter on them, so it doesn't help tell you if the rule is true. But participants are very drawn to this particular option, and Wason's proposition here is that this is due to a feature of human reasoning that he calls confirmation bias. So confirmation bias can be defined or understood as tendency to seek out information or form hypotheses that confirm already held beliefs. And this is one of the most consistent and replicable findings in human psychology. And confirmation bias is important not only to understand kind of performance in something very abstract like the Wason selection task, but to understand a lot of macro type behaviors. I mean, you can just consider today's debates, the contemporary debates about an increasingly polarized political landscape, where people on social media are thought to be in kind of filter bubbles where we kind of only seek out information from if we're a left-winger, we seek out information from a left-wing source, and if we're right-winger, we seek out information from a right-wing source. And these kind of tendencies, which I think quite rightly have been described as problematic for our democracy, are just further examples of confirmation bias. So this idea that people will form an idea or hypothesis and then seek out information that confirms their worldview. If you think vaccines are a good way to combat childhood diseases, then you of course seek out information from established medical sources saying that vaccines are good. And of course, if you're an anti-vaxxer, then you'll go on to alternative news media sites and seek out information that'll tell you that vaccines are terrible and give you autism and whatnot, right? So let's review some more experimental demonstrations of confirmation bias to kind of cement our understanding of this phenomenon. So in one of Wayson's earlier experiments on confirmation bias, he presented participants with a sequence such as like 2, 4, 6. And then he would ask participants to think of a generating rule and then write that down on a piece of paper, and then give a sequence that they tested their hypothesis about the generating rule, and the experimenter would kind of give a positive or negative feedback if that sequence matched the generating rule that the experimenter was thinking of. So in a sense, this is a bit of a game like when you're traveling somewhere and someone's thinking of a person, and if you have to ask them questions and they answer yes or no to that, but with sequences of numbers. So for example, the participant here is 2, 4, 6, and then thinks of a generating rule, and if you're like most people, you probably think that this means that the sequence incrementing in 2, so maybe they'll say 10, 12, 14, and the experiment will say yes, this conforms to the rule. And then the participant will say, well, maybe 98, 100, 102. The experiment will say, yes, this conforms to the rule. And then the participant, when they're ready, they will say, okay, I will guess the generating rule. The generating rule is a sequence going up in numbers of 2. But then the experiment will say, no, that was false. And the reason for this is that the rule that the experimenter is using is any ascending sequence conforms to the rule. Now, however, what most participants did would be something like what I just verbally described to you. They would tend to test more specific rules in a confirmatory manner. And even if they would kind of diverge from this pattern of increasing in 2, or maybe test something like 5, 15, 30, that would still conform to the experimenter's rule. And this is the reason because the participants will usually think of a generating rule, and because of confirmation bias, think of sequences that kind of confirm their expectation. However, very few participants would do what optimal strategy in this case, and that is to, whenever they have a possible rule they think is true, is think of possible disconfirming instances, such as a sequence of 5, 5, 5 or 3, 2, 1, which would give them much more information about the actual rule that the experimenter is thinking of. And this is another case of where we see that due to confirmation bias, we have a problem to seek out falsifying instances to the hypothesis that we're currently entertaining. And reconnecting to the kind of political importance of confirmation bias, in one study, participants were just taken to a computer lab and surfed a controlled online forum that had articles relating to their political opinions with information that would either confirm and disconfirm their political opinions or other attitudes. And generally it was found that 36% more time was spent reading attitude confirming versus attitude disconfirming material. So also in these kind of ecological valid settings where participants are not doing a contrived task that, like, generating number sequences or doing the Wason card task, predictions of the confirmation bias framework are kind of upheld. So given then that we have this kind of pervasive tendency towards confirmatory reasoning, why is it? So there is no definite answer to this, but one kind of persuasive theory that's been proposed recently in the past kind of 7-8 years was known as the argumentative theory of reasoning. And on this theory, reasoning in humans has evolved to facilitate communication, and particularly persuasive communication. So the idea here is that one of the sort of reasons we evolved an ability to kind of reason abstractly about things and so forth was to convince other members of our social groups to do things that we wanted them to do. For example, if we're choosing to forage for berries or hunt for rabbits, then, you know, depending on my preferences, I will want to convince the rest of my group to do one or the other task. The idea is then that in order to be really good at this, we need to, when someone says, well, we should hunt rabbits because rabbits are tastier, then I want to say something, well, that's not a good reason for choosing to hunt rabbits. We should choose the food that has the highest energy gain versus energy spent ratio, for example. The idea is then that on argumentative theory of reasoning that we kind of evolved a reasoning faculty that was very good at detecting bad reasoning in other people, but very bad at detecting bad reasoning in ourselves. Because of course, if I'm trying to convince you about something else, what will help me the most is figuring out quickly evidence for my position, so seeking out confirmatory evidence. So on this account, then, confirmation bias and other features of human reasoning, such as motivated reasoning and reason-based choice, can all be seen as kind of expected features of this kind of evolved argumentative device that is biased towards detecting faulty reasoning in others and seeking out support for one's own position. And there have been some attempts to try to test predictions from the argumentative theory of reasoning. And one example is the study that's described here. And this was a kind of a reasoning study. So participants read these kind of logical problems, as you see up here in the first phase bit, and they gave a response. And then they also wrote a short statement about why they chose that response. So they kind of explained gave an argument for their response. Then the experiment transitioned into a second phase where participants were told that they would see their original answer, they would see another participant's answer, and that participant's reasoning. And then participants were told that they were allowed to change their minds if they wanted to about their response. So the idea here is like the cover story is like that. I give a sort of response to a reasoning question, and then I see what someone else has answered, and then that helps me hopefully change my mind about my position. Now, critically here, there was a non-manipulated condition and a manipulated condition. So in the non-manipulated condition, participants saw their actual original answer, and then they saw the answer of some other participant and their reasoning. In the manipulated condition, however, participants saw someone else's answer inserted as their own, and then they saw their own answer inserted as the answer of another participant. So the idea here is that here in the kind of non-manipulated condition, the participants are evaluating someone else's answer, which is actually someone else's answer, and judging that in relation to what they've kind of think they've originally answered and the kind of information in the problem, while in this other case, they're actually evaluating their own answer, believing that it is someone else's. So there are many results in this study, and I'm just going to highlight a few of the central ones. And one very, very important finding here is that participants, it turns out, reject their own arguments about 56% of the time. So when they believe that an argument that they just a few minutes earlier gave in support for their own position is someone else's, then they are quite likely to reject it. And of course, needless to say, when not manipulated, they quite often kind of go with their original position. And that, of course, gives support to kind of the main prediction from the argumentative theory that people are kind of selectively critical of arguments as predicted. Interestingly enough, if you look at kind of the overall performance, if at the end the participants got the correct response, it turns out that this kind of selective reasoning leads to an improvement in the participants' performance, since if they originally made a mistake and they see it being presented as someone else's argument, and they of course then start they're motivated to reason against it, then they usually end up in a with a correct answer to the problem. So it turns out like by turning the participants' own reasoning against them, their original arguments, and making them more critical, it helps them perform better in the task. And has been proposed, and there's some preliminary work testing this, that this might be a way of helping students perform better in tests by letting them first do a test and then look at the test answers thinking it's someone else's and correcting it, but in fact correcting their own answers, and then handing that in as a final test response. And that might prove a better and stronger test of the actual knowledge a student possesses, because due to confirmation bias, students will quite often give a response to a test and then fail to kind of think it through properly a second time, because it's very difficult to search for this kind of falsifying information for humans. We're now going to transition to start talking about and considering another fallacy of human reasoning, and this one is the base rate neglect. And this one is slightly more mathematical and complicated than, for example, confirmation bias, but we'll look at a few examples and hopefully get a good idea for what it means. So base rate neglect is defined or understood as a situation where people ignore the information of the base rate of something occurring and instead focusing on specific information pertaining to the situation. So let's look at a quick example. Imagine someone saying the following about their child. Only 6% of applicants make it into the school, but my son is brilliant. They are certainly going to accept him. So what might be the problem with this line of reasoning? It certainly isn't that the parent's judgment about the brilliance of their child is wrong. Instead, what the parent is doing here is ignoring the information that the school is highly selective, meaning that likely of the children that do get accepted, all are brilliant. In other words, the base rate of brilliant children getting accepted into school is very high. Therefore, the information that the child is brilliant does not strongly support the parent's claim. So the parent is kind of focusing on this 6% here, while instead should be focusing on the actual students who get into the school and what their characteristics are. And this kind of base rate neglect is particularly common for probabilistic reasoning, to the extent that's been proposed that humans are really bad at probabilistic reasoning. And we're going to look at another example, which is one of the most famous examples in the psychological literature on base rate neglect, to further examine this point. So considering the following case. If a test to detect a disease whose prevalence is 1 in 1,000 has a false positive rate of 5%, what is the chance that a person found to have a positive result actually has the disease, assuming you know nothing about the person's symptoms or signs? So if this was a classroom, I would ask you to take a few minutes to think about this, and then we would discuss your different answers. Now, just pause this, think about it for a few moments, and then write down your answer or your guess, and then continue the video. So, unless you spent a lot of time on this or have a very strong mathematical background, you probably found this to be slightly difficult. And you may or may not have gotten the correct answer, which is 0.02%. So this is a case of probabilistic reasoning. So now we're going to next look at this question again, but formulated in a slightly different way, and hopefully you will have the intuition that this reformulation makes it simpler to solve the problem. So consider this case. 1 out of 1,000 Americans has disease X. A test has been developed to detect when a person has disease X. Every time the test is given to a person who has the disease, the test comes out positive. But sometimes the test also comes out positive when it's given to a person who is completely healthy. Specifically, out of every 1,000 people who are perfectly healthy, 50 of them test positive for the disease. Imagine that we've assembled a random sample of 1,000 Americans. They were selected by a lottery. Those who conducted the lottery had no information about the health status of any of these people. How many people who test positive for the disease will actually have the disease? Once again, pause the video and think about this and think of what your answer would be. So hopefully you found this easier to reason about, and hopefully you reach the conclusion that the answer is 1 out of 51. So why 1 out of 51? So we get the information that 1 out of 1,000 Americans has the disease. So we know that one person will have the disease if we test 1,000, and it's a random sample. But we also know that there are a number of false positive cases, and we're told that there are 50 of them. So we know that when we've tested 1,000 Americans, we'll have 50 false positives. So there needs to be another 50 added to the one given here. A common mistake, I think, for a lot of people on this, even in this kind of frequency layout of the problem, is to forget to add the 1 then back to the 50. The examples that we looked at the previous slides have been widely replicated with various formulations and various tests, and the kind of standard finding in this literature is that people are simply much better at reasoning with frequencies compared to probabilities. Unfortunately, it is not really known exactly why this is the case. And there have been proposals for deep evolutionary explanations for this. There have also been proposals about this has to do with neuronal architecture of the human brain, but there is no really good current theory or explanation for why this is the case, but it's fairly accepted that when we're given probabilities, we often fall into base rate neglect, but when we reason with frequencies, we much more rarely fall into base rate neglect. Now, one particular situation that might lead to base rate neglect is something called attribute substitution. And attribute substitution occurs when we overemphasize information about individual cases, such as stereotypical characteristics. And a famous demonstration of this is due to Kahneman and Tversky, who conducted a test which is known as the lawyers-engineers experiment. So in this experiment, participants were told that they would hear a number of characteristics about people, such as that they're very bookish, they're very good at math, things like that. And they were also told that these people were drawn from a sample from a town which consisted of either 70% lawyers and 30% engineers, or vice versa. So participants belonged to one of two conditions, either a condition where they thought that the people were drawn from a lawyer majority town, or that the people were drawn from an engineer majority town. However, what Kahneman and Tversky found was that when people were given many cases of persons drawn from these towns, then they kind of judged very similarly if they thought this person was a lawyer or an engineer, while they instead should have been allow themselves to be influenced if the person was coming from a lawyer majority town or engineer majority town, so that the judgments between the groups did not differ when they should have, because simply looking at the individual characteristics is not informative enough if you know that there is a certain base rate of individuals existing in the population from which you're drawing the sample. So base rate neglect is a very important kind of flaw in our reasoning, and has important implications in diagnostic situations. Georg Gigerenzer, who's the kind of guy who's developed a lot of the research on base rate neglect, has found that doctors, a lot of this work is done in Germany, have problems thinking about the correct false positive and false negative rates for diagnostic screening, such as mammographies or for HIV tests. And of course, this also has implications for clinical training in psychology, and thinking about the base rate incidence of certain types of psychological psychiatric conditions in the population when considering the outcomes of a diagnostic test. So this concludes this lecture on problem solving and reasoning, and we've blitzed through a lot of material and covering wide ground, and there's of course even more covered in your books, especially on reasoning and heuristics and various other fallacies. Yeah, if you have any questions or you're wondering anything, then please do email, and I'll try to get back to you with answers as soon as possible.